Okay, can everyone hear me? Great. Yeah, I'm presenting joint work with Alejandro Serrano and Julian Hage. And in this work, we sort of explore the design space of, or what we can do with type-level programming in Haskell. And so there's a long history of advancement in GHC of what we can do in terms of type-level hackery, right? I mean, going back all the way to type classes, but then functional dependencies allowed us to do some kind of type-level programming already. But then once we had type families, and especially closed type families, could do even more on the type level. And with the introduction of data type promotion and kind polymorphism, we even have a language of types that we know and love already on the term level. And so in this work, what we wanted to do is sort of use these type families and see how we can use them to simulate type classes, and what there is perhaps to gain in terms of flexibility of the kind of search for instances, for type class instances, and also of expressiveness. So I start off with a simplification where I look at the problem without considering the class methods and only view type classes as predicates on types and see how we can simulate type classes using type families. In the middle segment of the talk, I'll be telling you about what we can do once we have this kind of encoding. And in the last bit, I'll give you two ways of how to introduce then class methods, really. Well, because that's what type classes are all about. And in particular, I'll give a proposal of what we can do if we, for example, have something like elaboration for type families. Okay, so how do we encode type classes? So as I said, we make a simplification here. We view them as predicates on types. And it's pretty easy. So if we have a type class, an n-ary type class, then we simply encode this as an n-ary function to bool, right? So the characteristic function of the relation that it defines. But actually, I will not use the bool here, but instead this kind or this promoted data type here, which is isomorphic, which just says yes or no, because later on I will refine this type so we can add additional information here. So we have defined here. So in the end, we have this here. So we define a type class like this as a characteristic function from the n arguments to defined. And just a quick example: if we have the type class EQ, well, for now we just ignore the class method, then we define this type family which goes from this type variable A to defined. And if we actually want to use it, so for example, if we have a function here that has EQ in its context, then instead of having this, we say is EQ of A equal to yes, right? We ask this question, or we can also just define this type synonym where we say this is equal to is EQ equal to yes. Then we can write it in the same way. So how do we actually define the instance declarations in this encoding? So here's a couple of examples that we usually have for atomic types, list types, and products. And this is how you would write it down in this type family encoding. So for int, we just say, well, yes, there's an instance. For lists, well, we have up here we have a dependency on the context A, and then we just say, well, it is whatever this will give us. And whenever we have more than one constraint in the context, then we have to compose the two constraints that we have here. So we have a conjunction here, so which is simply a type family, closed type family, which we define to be a conjunction. Right? We want to have both sides to be true. This is fairly straightforward. And we can also do other stuff. We can encode superclasses like this. We find that in the paper, and also limited forms of functional dependencies, which in fact requires injective type families, which we have seen yesterday. And they're limited because, so we've seen yesterday that there's this connection between these injective type families, in particular these declarations of injectivity and functional dependencies. But not all of these injective declarations are supported, which we need in order to really encode functional dependencies in a full way. What we do not support is overlapping instances, but as I will show you, most use cases can be encoded using similar things like instance chains, which we have seen yesterday. Okay, so what else can we do with this kind of encoding? So I'll give you three examples. The first one, which is known as type class directives, so where we can restrict the kinds of instances that we allow. The second one will be custom error messages, so we can attach additional data to this data type defined in order to say why we failed to find an instance, and then I go to instance chains. So these type class directives, we can say explicitly, no, I don't want to have an instance, for example, for the function type. We don't want to be able to show this. And we then get an error message that clearly says, well, you can't expect that function types are showable. Right? And later on, we add a little bit more data to actually give you a message of that. The second one is you can also define a set of closed instances. So sometimes you don't want to have open classes. For example, here, where we have this integral, where we perhaps only want that integers and int are instances of this type class, where we can define a closed type family like this and say, well, we only have that these two are yes, and for any other type we want to have no. And we get a corresponding error message. Second one is disjointness. So sometimes we don't want type classes to have overlapping instances. For example, here, where we don't want whatever is an integral instance to be a fractional instance, and vice versa. What we can do is instead we have a function which sort of decides whether a type is integral or fractional. Right? So we give a bunch of rules which says, well, int really should be an instance of integral, integer also, but double or fractional. And then we wrap this up like so, and define that is integral as, well, first we check what this function is integral or fractional gives us, and if it is an integral, then yes, and otherwise we know, well, we can't provide an instance like that. Okay, we can also provide additional error messages. So this was the type of defined, and what we can do is we can add some additional data to the no case, where we say, well, it is no, but perhaps I want to give you a reason why the answer is no. Like, for example, in the integral example we have seen earlier, we can, for example, say that in the case that we find that something is instance of fractional, we say no, and then we can say, well, you cannot expect that to be an instance of integral because we already seen that it is an instance of fractional, I should say, not fractional. And you get a corresponding error message that would say, well, I can't match no with the error message here with the type yes. So we can't find an instance of integral for double. Lastly, you can do things like instance chains, which we have seen yesterday, which provide you kind of an explicit means for failure, where you say, well, I don't want to have an instance here, but also give you a means to give alternatives, where you can do backtracking through different instances. And a very simple example we can give for show here, where we want to be able to give an instance of show for function types if A is enumerable, so we can give sort of a table of the function, right? And then we can give a corresponding instance of show, and otherwise it immediately fails, right? And so we have this sort of this if clause here, and otherwise, and you have this else here. We can have arbitrary deep chains of this, and we can encode this as type families again, where we have this explicit check. So we have this type family which explicitly checks whether the first one is an enum, this one is a show, and this one is a show, and then takes the conjunction of this. This can be generalized to deeper chains. But yeah, I've been ignoring all sort of the whole point about classes to begin with, right? What about class methods? And there are several ways to deal with them. So in the paper, we sort of give two examples how we can do with this. The first one is sort of an escape hatch saying, well, we can use type classes. I mean, the idea is that you would encode all these features like type directives using type families, do all this backtracking search, and then use type classes to generate your dictionary of functions, right? So if we look at the result that these type families will give us, it will give us a yes or a no, right? We can, in the yes case, we can give it an additional piece of data, which will be the proof. Give it a proof object that says why we said yes, right? And then this proof object can then be used for the type class instances, where we can sort of replay the choices that we have made in the search procedure. Well, you find that in the paper. I'll talk more about the second bit, which is the more out there idea about extending type families with elaboration. So the idea is to assign dictionaries to type families, and as you do rewriting according to the type family definitions, these dictionaries come into scope. That's at least the idea. So let's look at an example again. So we have a type family is EQ, and in addition to saying whether it's defined or not, we also give it a method, namely the equality method, right? So whenever we give an instance, for example, for the integer, then we give it also an implementation of the dictionary. Here it's rather boring. For something more interesting, for example, lists would have something like this, right? So we want to say that we have an equality on list types whenever we have an equality on the element types as EQ. Then we have to construct this function that checks for equality on lists. And for doing so, we have to refer to the dictionary that we get from this recursive call of the EQ. This is what this syntax is meant to be. So we have this EAD, means give me the dictionary of for this type family at this type, which we'll use here to check for equality on the heads of the list. Here's another example where we try to implement data types a la carte using this method. So the idea is that we want to implement this one here, so that f is smaller than g. And to do so, we want to give an injection function from the smaller f to the bigger g. Now we go through the definitions here, so we have reflexivity, and so we have yes here, and the injection is the trivial one, and this one is here the interesting case. So here we want to do backtracking. We want to check whether f is either in the left of the sum or the right of the sum. And this is where this helper function choose comes into play. And here we have three different dictionaries that we have to play around with. So we want to say that this is true whenever this choose function is true, right? So that we define this to be equal to choose, and then we give it the two arguments. So we recursively check whether f is in x or f is in y, and then depending whether this is true or not, this will be decided down here. So this is the f of x and the f in y, and when it's in yes, when it's in the left-hand side, we return yes, and then the choice function, which we use up here, will then correspondingly try to do the injection into the left-hand side, and otherwise in the right-hand side. And otherwise, we return no, and we don't give a dictionary. But the important bit is that we have to explicitly refer to the dictionary that we potentially get if we check this recursively. Right? So we get either the one for the left or the right-hand side. And the tricky bit is that we only get one if this one is actually true. So this one actually returns yes, and this one returns, or this one returns yes, right? So ideally we only use one of these. We only use one of these two, right? Which is then used by the choice function, right? We only ever use the left one here or the right one here. That's why we have to explicitly name these dictionaries for each type class. That already brings me to the last slide. So I mean, there's lots of things still to be said about this elaboration. So there's no implementation at the moment. It's more like at the moment it's more like an idea of the syntax that we would write down in order to do the encoding that we would do by hand using type classes, right? Where we have to explicitly construct these proof objects and then dispatch on them by type classes. And so the idea is to have rather this kind of elaboration syntax to that. And then perhaps use this as an encoding for actual type classes in the back end. But this is still to be figured out. So in the paper you find encodings of the functional dependencies, how that will work out, the encoding of superclasses, and many more examples. And particularly you also find the proof of the soundness and completeness. So we have this translation from type classes to type families, and what we want is that they really capture the type classes. So we prove that this is actually the case in this outside-in framework. And with that, I'm happy to take questions.
So notationally, this looks almost exactly like functional logic overloading,
yes.
Which predates type families, so it uses a different evaluation mechanism at the type class level. Have you compared your approach to that?
No, we didn't. But that looks like a good way to go. I mean,
because I think
it sort of combines. I mean, it combines sort of the logical way of type classes with the functional way of programming of type families.
Yeah, exactly. So it uses pretty much the exact same trick of encoding type classes by their characteristic functions, and I think gives you very similar or even more expressive power.
Yes. Thanks.
So I know I'm sometimes guilty of taking functional dependencies and re-implementing them from scratch in type families, but this feels like sort of another step in that direction. I guess what I'm wondering is the encoding with the elaboration. What does that give us over instance chains?
That's a good question. I don't know. We haven't actually investigated what addition we get there, as opposed to instance chains. And I have to think about this. Perhaps in practice, you can always sort of rewrite your type family definitions in terms of instance chains. That might very well be the case. That's a good point.
Yeah, instead of rehashing.
I mean, you could also. You have also by giving this kind of characteristic functions, but with additional data, you can perhaps have more information that you use for both dispatching on constructing these dictionaries and also giving type error messages. But that can perhaps also be integrated with instance chains. So that's a fair point.
Thanks.
I was wondering so one of the things that's nice about type classes is you can have these default instance or default definitions.
Right.
Where it's like, oh, here's the obvious thing, and then if it's more efficient, you do it yourself. Do you have a story for that within the elaboration framework?
No, we haven't.
I don't want to pile on, so apologies. But I was interested in the elaboration examples. So for like the data types a la carte thing, it seemed like you sort of had access to dictionaries even when they didn't exist. So like the choose function was given sort of both both the left
yeah,
and the right side.
there's some implicit. It assumes that you can only use a dictionary whenever. Why don't we go just back to it? Whenever, so that's a problem, right? That you have sort of both dictionaries here, even though you only get one of them if you're lucky, right?
So have you thought about how to enforce that, or?
No. Okay. No, we didn't. Thanks.